Our last presentation of this session continues on the theme of pavements, entitled Selecting Preservation Alternatives to Optimize Pavement Performance. Our speaker is Buzz Powell. He's the Assistant Director for the National Center for Asphalt Technology at Auburn University, where he also teaches courses in pavement construction. Buzz?
Good afternoon. Well, it's great to follow Kevin on the program because of the work that we're doing together. I'm honored to be here and provide you with kind of an overview of the research that we're doing on optimizing the selection of pavement preservation alternatives. ODOT, the NCAP pavement test track has been around since we broke ground in '98. The first track was in 2000, and I've been very blessed to be affiliated with the program ever since we started it, and ODOT was one of our inaugural funding partners and has been a funding partner ever since we started the track. So Kevin mentioned the two test sections that are the balanced mix design test sections. ODOT is also participating as a partner in what we call our cracking group experiment, and in that study we're working to identify we're not just looking at the iFit test and the ideal test that he mentioned, but we're looking at a battery of tests in the laboratory that are supposed to assess the durability and the cracking potential of mixes. So we got test sections on the track, and we pulled a bunch of samples, a massive amount of material samples when we built those sections, and we're running a full battery of tests at a bunch of different aging characteristic conditioning, so that we can see what matches the differences that we see on the test track. And before I get into the preservation alternatives presentation, regarding the question about TSRs, if you don't know anything about the ideal CT test, the ideal CT test is essentially the dry side of the TSR test. So you can take half of the unconditioned side of a TSR test and analyze not just take peak values off those load curves, but look at the shape of those curves, and you can calculate a fracture index from ideal CT testing. So, and I'm very much on board with the idea that mixes have been too dry for a very long time, and that's the reason why I'm excited about this not just the BMD test sections, but the cracking study test sections, because I'm excited about identifying tests like ideal CT testing that can be run on mix as it's being produced. So instead of just focusing on passing volumetric requirements, will the mix crack? Will the mix rut? The actual mix that goes down on the roadway. And I think when we can change and get into that mode of mix design approval and testing, then we'll all be a lot better off. And that brings me to selecting pavement preservation alternatives. So what I'm going to do in my presentation is kind of give you an overview of our research approach. Show you quite a bit of test data that we have from our preservation test sections, and then give you some options for implementation of these findings. And I think you'll see that this is very practical research, and we're really proud of not just the BMD research that we're doing, but also the pavement preservation research. So I mentioned ODOT being a sponsor, going all the way back to the first test track that we finished back in 2000. When we started back then, we had, I think it was 8 states in the inaugural track. And if you count all the logos for the state agencies up there, now we're up to 22 states. We're really excited about that, because the more states that get involved, then the more cost effective it is for the states that are in the program. You'll also now see a lot of northern states up there, like Wisconsin and Michigan and New York. And the reason those states now are involved is because we have a partnership with the state of Minnesota, with Minnesota DOT, with their Minnesota Road Research Project, and we've got the same test sections that we've built down on your test track at NCAT. Now we've built those same test sections up in Minnesota, so we can have the hot weather version of the study and the cold weather version of the study and the extreme cold weather version of the study, so that regardless of where you fall in the country, there's some findings that are directly implementable for you, possibly some version of those two when you're in the states that see climate extremes. And the partnership with Minnesota includes the preservation study, but it also includes the cracking mix performance experiment, which directly relates to balanced mix designs. So we're extremely excited about the partnership with Minnesota, and which is now entering kind of its next phase in this current research cycle, which we call the 2018 track. So this type of testing is called accelerated pavement testing, or accelerated performance testing, APT for short, and there are different research facilities that attempt to do this type of thing all over the globe. Most people use some type of a load simulator, like a device called an ALF or an HVS, a heavy vehicle simulator. We use triple trailer train actual trucks, so you can kind of imagine that the track is a 1.7 mile giant outdoor laboratory where we've got, you know, the whole battery of tests that we can run in the lab, but the ground truth is what happens out on the test track. And we don't super load our pavement, so every axle in that eight axle train besides the steers is loaded up to but not beyond the federal legal bridge limit. So we're up to 20,000 pounds, but not way past that. You know, we could load to 30,000 pounds and fail pavements really quickly, but then the cracking results wouldn't necessarily mean anything when you try to implement those findings out on the interstate. So we run essentially with federal legal loads on our axles. We run 5 trucks at a time, 16 hours a day, 2 shifts of drivers. So each one of these trucks does about 400 laps a day, you know, times 5, and we do that 5 days a week. So we shut down 1 day a week is everybody's day of rest and worship, and the other day is data collection. So, you know, I kind of grew up in Alabama DOT. It's interesting I'm here on the program because I told the first presenter I interned in geotech and did bridge construction, but I grew up in Alabama DOT and did a lot of work in pavement management, pavement parameters, data collection, and I really enjoy being able to shut the fleet down and go out on the track without having to look over my shoulder to try to keep from getting run over. So that's a very important benefit of the research that we do on the track. But we run about 750,000 miles a year in order to compress a design lifetime of damage into about 2 years of fleet operations. So in these 3-year project cycles, we have construction at the beginning and destructive forensics at the end, and then 24, 25 months worth of fleet operations in the middle where we run for a week and shut down and do all of our pavement condition assessments, and then run for another week, and we work our way throughout the 2 years in that manner. So with that kind of as our business model, as our research model, we really are a nonprofit business at the National Center for Asphalt Technology. You know, we just do research for cost recovery. We don't get any kind of a funding allocation. We sell test sections on the track to state DOTs and to FHWA and to private sector partners. But our mission at the track is really, it's kind of a threefold, 2 primary things I would say are our mission. We help state DOTs implement positive change, and I came from a state DOT, and I know it's really hard to make significant changes on the open network, because when you make a change in the wrong direction, it can have multi-million-dollar negative consequences. So we can do things on the track to help bring about that change at very low risk for state agencies. And what we really like to do is to promote real innovation for industry. So we kind of stand in the gap between state agencies and industry, and I think balanced mix design is a good example of what I would call real innovation. You know, that's something where you got a lot of private sector companies out there who they want to build good roads, but they're in a competitive bidding environment where, you know, you're bidding at lowest cost against competitors who are all going to be trying to blend materials and produce materials at the lowest possible cost. So you got a lot of companies out there that are like CRH that are leading the charge for balanced mix designs, because they want to build good roads, but they've got to do that in an enforced competitive environment. So we really think BMD is going to be real innovation for industry and for agencies. And the overall goal is safe, sustainable, and cost-effective flexible pavements. That kind of is our mission in a nutshell. There are 3 areas of research that we do. And when we started the first track back in 2000, the first one that y'all were involved in, we did a study of first generation super pave versus V mix designs, because you were in transition between one and the other, and you wanted to know how it would perform. So first track was a big study in mixing materials, and then that kind of evolved into at all the different layers in the pavement structure, what are the ideal combinations of materials in each kind of targeted specific layer. And that led us into structural pavement design. So where the first track was a big, thick perpetual pavement, we started tearing test sections out and building thinner pavements to do empirical design calibrations and mechanistic empirical validation and calibration, and it helped states to implement more efficient structural pavement design. And then finally we got into about 2012 pavement preservation. So it's kind of a holistic pavement experiment program now. What are the ideal materials in each layer? What's the optimized thickness of the whole pavement structure? And then what kind of roof do you keep on the house in order to achieve the lowest possible life cycle cost? So it's a very rewarding thing for me, being a state agency guy, to do this type of research. And what I'm going to focus on for the bulk of the presentation is pavement preservation. What do you do to the roof on the house with the funds that you have in order to continue to provide safe mobility at the lowest possible life cycle cost, or as close as we can get to it with the funding limitations that we have? So if you think about kind of this theoretical pavement condition curve, where pavement's in really good shape when you first build it, and then it deteriorates over time, and when we can do things to it when the curve is relatively flat, we call that preservation. And then when it starts to deteriorate rapidly, we got to do rehabilitation work. And then finally, down at the bottom of the curve, you got to rebuild. That's reconstruction or deep type rehabilitation. So if I superimpose on this the ASTM PCI scale that shows going from good to completely failed down at the bottom, if you're just doing a sort of a worst first reactionary type of a maintenance and reconstruction program, you start with the lightweight stuff up top, and as the pavement deteriorates, you go to different alternatives that cost more and more as you go deeper into the pavement structure. But when we talk about pavement preservation, we don't want to go deep down on that curve. We don't want to go far down on the curve. We want to stay up near the top, and when we can stay up near the top, what we really want to do are select those alternatives instead of just starting with the lightweight stuff and working our way down. We want to choose the alternatives that are going to help us to achieve the lowest possible life cycle cost, the lowest cost per lane mile to preserve the structure. So some of y'all might be familiar with the Strategic Highway Research Program version 2, the R26 product that came out of that, and essentially it's a matrix to help you to provide some amount of guidance as to what types of treatments you can use on a roadway, preservation treatments you use on a roadway. And that second column there is the PCI scale that I showed you superimposed on the right on that last slide. So essentially all this shows you is sort of a multicolored, broadened version of the slide that I showed you previously. And what I want to illustrate here is if you highlight microsurface and then thin lay surfaces, you know, that tells you what's possible to choose, and it tells you what not to choose, but it doesn't really provide you any kind of guidance on cost per mile, like what is the best investment in terms of a cost per mile. If you look at what the FAA has done, they've kind of expanded in some ways the ranges on that table, and they said, okay, well, for poor condition, fair condition, and good condition, it acknowledges that if you do preservation on a road that's got a bunch of distresses on it, it's not going to last very long. But if you do preservation on something that's high up on the curve, it can last a pretty long time. So this was our starting point, because our thinking in our experiment was, what if we can tighten up those age ranges so that when you're selecting alternatives, if you're a state agency or a county or a city, you can look at your costs per mile or cost per square yard for the different treatments and plug these ages in based on the pre-treatment condition of the roadway, and then pick whatever works best for you in a way that's not political, but is just based on cost to maintain the infrastructure. So that led us into this preservation experiment that we started back in 2012, and we put some test sections for preservation on the test track under accelerated traffic, as I described earlier. But the main parts of our preservation program are Lee Road 159, which you may have heard about. It's kind of a world-famous little county road now. And then US 280. Lee Road 159 was a dead-end road to a quarry and an asphalt plant where empty trucks were running in and loaded trucks were running out. And it was 14 years old. Since the last work was done on it, and the local county just gave us that road and said, you know, put whatever test sections you want to put on it. So we put all kinds of stuff on it. And then 3 years later, Alabama DOT gave us 4.5 miles of US 280, about 5 minutes from the test track, and we did the same thing out there. So we did thin lays, we did microsurfaces, chip seals, crack seals, fog seals, and then all kinds of different combinations of those. And we did them without doing any kind of significant work to the roadway. We just went out and mapped all of our pretreatment distresses: roughness, rutting, texture, cracking, deflections. We measured, you know, everything that we could think to measure to help us wrap our arms around what is the true pretreatment condition of these test sections. And then we put these treatments out, and then we started to monitor the recurrence of those distresses in these sections so that we could relate, you know, quantify the life extending and the condition improving benefits as a function of pretreatment condition. And that was good for the hot climate states. We needed to do the same thing for the cold climate states. And again, that was one of the reasons why we had a big expansion in the number of states that participated. So we built all the same test sections on a county road up in Minnesota, County State Aid Highway 8, they call it, up in a little community called Pease, Minnesota, and then US 169. And there's a T intersection right there where both of those roads connect. That was our staging location when we built all these sections, and we moved our whole operation up to Minnesota. So I stayed up there for 2 months, and we moved our portable laboratory up there, mobilized our contractors. So it was really a unique opportunity to have regionally appropriate materials, the same contracting team, the same inspection team, the same design effort, and the same construction effort. So we did exactly the same work up there that we did down south, and achieved a really high level of quality. So how many of y'all are familiar with MAP 21? Raise your hand if you've heard the term MAP 21. Okay, that's essentially for most of us, that's a system that's in place now with the federal government, where the federal government says we need you to maintain your infrastructure, state agency, at a minimum level of condition, and if you don't maintain it at a minimum level of condition, then we're going to come in and help you prioritize how you're spending your money to help you manage it better so you can do it. So you know, the state agencies all want to stay up in an acceptable range because they don't want to have to lose their right to manage their funds. They want to continue to spend money the way they choose. So it breaks down pavements in terms of poor condition, fair condition, and good condition, and it specifies ranges for flexible pavements, for cracking, for rutting, and for IRI. So what we found with our research, we measure all of that in our test sections, but roughness really doesn't change until a pavement is in a failure condition. Otherwise, it's pretty flat. Rutting doesn't change again unless something's going wrong, you've got a material deficiency, or it's in a failure condition. So what we're seeing more than anything else is the return of cracking in our test sections. And so that's the thing that you hear us talk about the most when it comes to implementation of our findings. So what we're doing is we mapped all these parameters before we put these sections in, and now we're monitoring them weekly, just like we do our test tracks at NCAT and at Min Road, and we're looking for the recurrence of all these parameters, but specifically cracking. That's the thing that changes the most. And these are the types of curves that we're generating from this research. And this is from Lee Road 159, but we're monitoring the data in exactly the same way on US 280 down south, and then County Road 8 and US 169 up north. And what you see on this is the solid lines are the cracking plots with the treatment applied, and the dashed lines are what the cracking levels would be if the treatment had never been applied. So the separation between those lines is really the effect of the treatment. And this has about 5.5 years worth of data in it. This summer is 6 years, and we have to go through a vetting process with the data. But what this shows you is the green line is when it was in pretreatment good, the yellow is pretreatment fair, and the red is pretreatment poor. So immediately some stuff jumps out at you on that, and you see that when it's in poor condition and you put a lightweight treatment on it, in this case a single layer microsurface, it drops down really quickly and cracking comes back. That's no big surprise. We expect that to happen because microsurface is a relatively thin treatment. But the reason why I wanted to show this to you is because the x-axis offset, in this case for the yellow line there, that is the shift in the pavement life cycle curve in terms of cracking. That's the life extending benefit, and then the y-axis shift is the condition improving benefit at any point in time. So we've got a curve like this for every unique treatment and unique treatment combination broken down into the MAP 21 criteria, where it's shaded in red for poor, pre-treatment poor, yellow for fair, and then green for good. And that green is just a sliver up top because it's 5% or less of the area cracked. So I'm just going to step through some of the treatments and treatment combinations that we have. That's single layer microsurfacing. Look what happens when you go to double layer microsurfacing. Completely changes performance. And this rapid reflection of cracking that you expect with single layer microsurface, when you do a double layer microsurface, you don't see that at all. Now you got a lot more cost associated with that because now you got to make multiple passes, multiple lane closures, so it's a more complicated installation, but the benefit of the double micro is very very apparent there. There's a single layer chip seal with crack sealing. It's interesting there because you see that if it's in pretreatment good, the green line is flat out there, but if it's fair or poor, those lines are tracking right along on top of each other. And so the way the curves are banding together, good and fair or fair and poor, that's telling you something about the robustness of the treatments and the treatment combinations. There's a Pavement chip seal. I don't know if y'all do any of that here, but it's a chip seal. It's got fibers that are sprinkled into the emulsion shot, and then you come in and apply the chips and roll that material down. And we've seen excellent cracking prevention from Pavement chip seals, as you can see in that plot. This is a double layer chip seal, so even better performance than the single. And then there's a triple layer chip seal. So the more passes that you make with these treatments, the better prevention of reflective cracking that you see in the treatments. This is a virgin thin lay with neat asphalt with the regionally appropriate AC grade of 67, PG 6722. It's a mid-grade down in the southeast. Excellent performance, and at about 4.5 years, you start to see some return of the cracking reflecting in that 3/4 inch, 80 pound per square yard thin lay surface. That's with all virgin aggregates. When you go in and run it as a 50% wrap thin lay, and that's 50% wrap with a 54% aged binder replacement, aged binder ratio, so that's got a lot of really stiff aged binder in it. You see that the good and the fair are kind of trending down together, but the poor, there's quite a bit of separation with the poor, and after 4 years, you're back down into the MAP 21 poor range, and that's because it's loaded up with it's got really, in this case, from a balanced mix design perspective, it's got too much wrap in it, but we did this because we wanted to see what would happen on the roadway. Likewise, with all virgin aggregates but 5% shingles, and these are post-consumer recycled asphalt shingles, it does pretty well on the poor side until you hit year 4, and then because of all that aged asphalt in the shingles, it takes a nosedive and starts to drop off. So there's a lot of really good information in these plots, as you can see. And because of what you see when you go to 50% wrap or when you go to 5% shingles, which is because shingles have a really high asphalt content, that's about a 19% aged binder replacement in terms of this mix. This is one of the reasons why balanced mix designs are so important. So to kind of take a step back from that just a little bit, that's why we need to do this cracking group research to support balanced mix design implementation. So for states like Oklahoma and all the other states, we can identify which tests actually predict the differences in cracking that we see in our test sections and which tests do not. The two that I'm really interested in, because my focus in balanced mix design is all about construction. We need sophisticated aging, and we need sophisticated tests potentially to approve mix designs. But I'm a big advocate of running these tests at the time that the mix is produced and placed on the roadway, and that way, when you're tempted to run a little bit on the dry side, that's gonna jump out and bite you and cause you to take corrective action and prop back up that fracture index number or whatever test it is that you happen to be running. It's shown here on this slide as inflex factor, but inflex factor is the same thing really as the ideal cracking test, which is the same thing as the dry side of the TSR test, the unconditioned side of the TSR test. Contabro testing is the ultimate simple test, and we've seen kind of the same ranges of numbers that Kevin mentioned in his presentation, where like most of our mixes will run in the 5% loss range, and then we have some that run over 10%, and we're thinking that there's going to be a way to correlate the percent loss to the durability and the cracking performance on the track. But where in TSR testing, on the dry side of a TSR test, where all we're doing traditionally is taking those peak values off for the strength calculations, when you look at fracture index, what you do is look at the area under the curve, and you divide it by some estimate of the post-peak slope, and then that creates this index value, this fracture index value, where the higher the number is, the more ductile the mix is, the greater area under the curve, or the flatter the slope coming out of the curve, and that's an indication of mix quality. So what we've seen so far in our cracking group study that ODOT is a participant in is that all of the cracking tests, all the fracture index tests seem to relate to each other pretty well, and then the aged seems to relate to the unaged pretty well. So like if you guys could potentially use iFit to approve your mix designs, which take some sample preparation, take a little bit of time, and then maybe you use just a Marshall press with an IDT, the dry side of a TSR test, to monitor construction. That's a potential option because the numbers tend to relate to each other. In order to test drive this, when we built the track this summer, for every mix that we put on the track, we processed that sample the way we would do it if we were monitoring for cracking during production, and what we found was that within 3 hours from the time we pull a sample, we actually had an unconditioned IDT fracture index number, an ideal cracking test fracture index number that we could use to assess the quality, the cracking performance quality of the mix. And that's 3 hours is very implementable. So if you have a contractor run mix in the morning, by lunchtime you know what your fracture index is, and if it's low, you either got to increase the asphalt content or decrease the wrap content, or maybe put some rejuvenator in it, take some kind of corrective action in order to stay out of a penalty, for example, in your specifications. So to go back over to preservation, I showed you all those curves. Now how do you implement data from those curves? Well, this is a table that I put together that shows how many years did it take to get back to MAP 21 poor if the pretreatment condition was poor, fair, or good using the MAP 21 criteria. So we're still collecting data. We're in long-term data collection mode, and so within this research cycle, the 2018 track, we're collecting data every week in all 4 of our test locations, the 2 southern locations and the 2 northern locations. And as you can see, most of our test sections haven't gotten down to MAP 21 poor yet. It's the more vulnerable treatments are the ones that where you see numbers where it's already slipped down to MAP 21 poor. All the other cells, at some point greater than 6 years, because that's where we are right now, will it be back to MAP 21 poor? Another way to look at the data while we're waiting on all those other numbers to come about is this shows the reduction in cracking, or the separation between the solid line and the dashed lines at year 5. And what's interesting about this is if you compare all those numbers, the double micro, the triple chip seal, and the virgin thin lay are all showing about the same reduction in cracking for pretreatment poor, pretreatment fair, and pretreatment good. So that you can use these criteria to over budget cycles if you're a state agency or a county agency or a city in order to select preservation alternatives that provide the lowest life cycle cost for you. And I know I'm out of time. I wanted to end up by saying at the end of every 3-year research cycle, we host a conference. The most recent one was in March of this year. And for the current cycle that we just built this summer, the next conference, the next 3-year conference, has already been scheduled for March the 23rd through the 25th of 2021. So we would encourage y'all to come down. I think the people who were there for this really got a lot out of it, and we kind of go through our whole research program and roll out the findings.
Sure, I'd be happy to. In realizing technology advancements, what examples may you provide how asphalt pavement has improved since the year 2001?
How has asphalt improved since 2001? A good example Kevin alluded to in the last presentation, when we first built the track, the design gyrations, the high-level design gyrations in the super paved tables was 139, and we actually built test sections this summer for one of your state partners with 35 gyrations for design. So coming up with a more suitable level of compaction in the laboratory is a good example, kind of low-hanging fruit example of what we've improved on, because we're not crushing rock in the laboratory in order to come up with standard laboratory compaction. But in my opinion, the holy grail for us is getting the right amount of healthy binder in our mix, not approving or not building dry mixes that you asked about earlier. And I think that we're right on the verge of the most significant improvements that will be made in my career, that I think they're going to come about because of these cracking tests that we have now and balanced mix design practices.
The next question ties to our presentation from this morning. Do your truck drivers have any sort of platooning system in place?
We do. Auburn has a really active autonomous vehicle research program, and there's research that's being done on the track outside of all the pavement research that we do for the Department of Defense. We have not used automated fleet technology within our fleet, within our production fleet yet, but we're in the process of procuring an autonomy-ready tractor, and we're going to very carefully implement that technology within our fleet operations. And I'm very cautious about that for drivers for whose safety I'm responsible for, because when we're in transition between fully human-driven trucks and fully autonomous trucks, I'm going to have a driver, like this first truck that I buy, I'm going to have a driver sitting in that truck. And he's going to be sitting there for an hour, up to an hour at a time, potentially with no human intervention. So what I'm concerned about is when a glitch occurs, is my driver suddenly going to become, in milliseconds, is he going to take command of that vehicle in a manner that protects his safety? I'm concerned about the human factor side of it when intervention is required, because I don't want any drivers to run off into the woods and not make it home safely at night. So we're being very cautious about implementation in our production testing, while at the same time we're very active with a lot of the fleet automation that work that's being done.
The next questions are on the screen over here to the left.
I'll see.
You're right.
Which one applies to me?
The field picture of rutted asphalt that you had with the straight edge across the rut.
Yeah, I think that was Kevin's question.
Okay. It seems that the base layer types under these test sections would vary greatly. How is it determined whether the base layer is responsible for an earlier than expected failure?
That's a good question, and in our pavement preservation sections, they have all the same buildup. So Lee Road 159, US 280, and then the test sections up in Minnesota, you can't have the surfaces being confounded by different supporting materials, but they're all set up from end to end in a uniform manner. But that's a really good question. And for example, on Lee Road 159, it's 5.5 inches thick, so it's as I said, it's an access road to a quarry. So with heavy trucking, 5.5 inches is kind of a good thickness where we know that we see performance differences, and that manifests itself as cracking in our test sections.
How may the Cantabro test be correlated mechanistically with cracking of asphalt mixes and pavement?
Well, the Cantabro test is more of just a torture test. It's not something that has a mechanistic correlation. But where I come down on that is, we really want to have a good mechanistic simulation of what happens on the roadway. I get that, but really what we need to do is not build pavements to fail. So a Cantabro test is more of a pass-fail type of a test. And, we're not trying to predict performance to 2 decimal places. We're just trying to prevent a failure. And the same thing's true, I think, for the fracture index cracking tests. we're not trying to model performance, we're trying to prevent failures. So those are two valid but distinctly different objectives.
The last one has to do with implementing CAV on the track. How drastic would your savings be by implementing that?
Well, our implementation process, in addition to being complicated by absolute necessity of protecting the safety of the drivers, when we're in transition, I'm going to have an increased capital investment in the tractor, because that autonomous vehicle ready tractor is going to cost me more money, but I'm also going to have a driver in it. So when we're in transition from fully human fleet to a fully autonomous fleet, we're actually going to be paying for twice the driver cost, part of it in hardware and then part of it in driver labor. So it's one of those things where we're a nonprofit business, and there's a sensible business thing that we have to do to be good stewards of all the state's resources like ODOT, but we've got to protect our driver as step number one. So those are good questions, though. Thank y'all.